Welcome to Stepping Motor Fundamentals class. Here are the objectives of the class. After taking on this class, we should be able to understand the fundamentals of the stepper motor. It includes the constructions, the types, and the control circuit. We should be able to know how to control the speed of the stepper motor. And lastly, we should be able to know how to control the angular displacement or the angle of the stepper motor. Here are the class agenda. First, we will have a review of electromagnetics principle that includes the Ampere's law and the Lorentz force equation. Next is we will have an introduction to motor that includes the motor description and the definition of power and torque. Next is we're going to dive in to the stepper motor itself. That includes descriptions, parameters, its types, and the difference between the unipolar and the bipolar stepper motor. Next is we will be discussing the stepping techniques, the full step, the half step, and the micro stepping. And lastly, we will have stepper motor control, which includes the control circuit and the implementation on the microcontroller. So let's get started with the review of electromagnetics principle. We have the Ampere's right-hand rule. The Ampere's right-hand rule states that whenever a current flows on a conductor, a magnetic field will be produced. The Ampere's law states that when you grab a current carrying conductor with your right hand, wherein the thumb points to the direction of the current, the direction of the magnetic field will be in the direction of the palm. This principle was further discussed when you study the general form of the Ampere's law, which is included in the fourth Maxwell equation. But we're not going into details with this. So I have here a coil wounded on a ferromagnetic material. A ferromagnetic material has a high possibility of passing of magnetic field. So when a positive voltage is placed on the left side and a negative polarity on the right side, it is expected that the current will be flowing in this direction. When we look at the cross section of the motor, what we can see is a dots, and X's. The dot signifies the current is going out of the board, while X means the current is going into the board. Okay? When we apply right hand rule on these dots and X's, we will have this and this. If we apply right hand rule, the Ampere's right hand rule to all the dots and the X's, we will be having a bigger magnetic field, such as this. Take note that the current or the magnetic field leaves the right side and it enters the left side, which means this would be a north magnet and this will be a south magnet. Now, what would happen if we reverse the direction, wherein the negative terminal will be on the left side and the positive terminal will be on the right side? It is expected that the current will be reversed. And likewise, if we check the cross section, the dots and the X's will also be reversed. And applying the Ampere's right hand rule on this dots and X's, it will be producing a bigger magnetic field, such as this. In comparison between the magnetic field before, now it leaves the left side and it enters the right side. That means the left side will now be the north magnet and the right side will be the south magnet. The magnetic field B is the product of the permeability of material and the magnetizing force. The permeability of the material is a measure of how material conducts or allows the passage of the magnetic field. In this case, a ferromagnetic material has high permeability. The magnetizing force is the measure of the current density or how much the current per unit length. But since this has multiple turns, the magnetizing force is multiplied by the number of turns. The magnetic field is measured in can be measured in Tesla, and the magnetic field intensity is in ampere turns or ampere turns per meter. Next is the Lorentz force. The next theory we're going to use is the Fleming's left-hand rule or left-hand motor rule and the Lorentz force equation. In summary, the Fleming's left-hand motor rule and the Lorentz force equations provides the direction of the force acted upon a current-carrying conductor when subjected to a magnetic field. Basically, the Fleming's left-hand rule provides the direction using our left hand, while the Lorentz force equation provides a numerical value of the amount of force and its direction. So we'll start with the Fleming's left-hand rule. Fleming's left-hand rule said that if you positioned your thumb, index, and middle finger in such a way that they are 90 degrees apart, where the middle finger points to the direction of the current and the middle finger points to the direction of the magnetic field, the thumb will be pointing to the force that will be acting upon on the current carrying conductor. While on the Lorentz force equation, we can calculate the magnitude and the direction of the force by taking the vector product of the velocity and the magnetic field. The result of the vector product of a two vector is a vector that is perpendicular to the two vectors. So the velocity here is the velocity of the charge, and B is the external magnetic field. So if we take the dot product of the velocity of the charge or the current and the external magnetic field B, if we can see a vector that is perpendicular with both the velocity of the charge or the current and the magnetic field, that will be the direction of the force. So basically, the Lorentz force equation is an equation that is describing the Fleming's left-hand rule. Okay, so let's try to animate this and look at this. So if I have a current in this conductor that is flowing from right to left, and I have a magnetic field, an external magnetic field that is going from north to south. So I have here B, magnetic field B, and the current I. So using the Fleming's left-hand rule, it is expected that the force will be going downwards. Similarly, when we reverse the direction of the current, such that it is now moving from left to right, and the magnetic field still going from north to south, so when the magnetic field will be in B, the current will be going from left to right, it is expected that the current or the force will now be going upward. Now, what if we change the direction of the magnetic field? So still the magnetic field will still be going from north to south, but in different direction. So the magnetic field will now be going south and the current will be going from left to right. It is expected that before it is going up, now the force will now be going down. Is there any question before I proceed?